Hello everyone, I'm Yaman Sanger, a graduate student in University of Wisconsin-Madison. I'm working with Professor Bhuvana Krishnaswamy at the W Connect Lab, and I'll be presenting our work titled WiChronos today. In this work, we focus on the problem of scalability in low-power wide area networks, also called as LPWANs. Let's consider a sensor network deployed in a farm where thousands of sensors are deployed at distances ranging in the order of kilometers. Each sensor communicates to a central gateway. These sensors are buried under the soil and replacing batteries is cumbersome, therefore the nodes must last for years. Now these requirements of energy efficiency, long range, and large scale can be generalized to a majority of in-situ monitoring applications. The growing need for LPWANs has resulted in a number of commercial solutions such as LoRa or SIG. The vast majority of low-power communication algorithms have low range like backscatter and RFID. Cellular networks can give us longer range, but they're power hungry, and so LPWAN solutions like LoRa, Sigfox, and NB-IoT have emerged as a compromise for both low power and long range, but then they're not particularly scalable. The size of the bubble represents the scale of the technology, and monitoring applications require scalability to support thousands of devices. Let's see why they're not scalable. In this figure, the color blue represents control parameters, green is a desirable effect, and red is an undesirable effect. LPWANs and other solutions for long-range communication operate at lower frequency bands and in narrow physical layer bandwidth to improve signal-to-noise ratio at a lower bandwidth. So narrow bandwidth is needed for long range. The downside to decreasing bandwidth is that the data rate reduces. This increases the time on air, which essentially is the duration for which the radio must be on, and that impacts the battery life negatively. At the same time, the total time for which the channel is being utilized also increases, and the probability of a collision goes up. Conversely, increasing bandwidth decreases time on air, and in doing so, helps achieve better battery life and lower collisions. We can see that the requirements on the coexistence of our desired properties of low power, long range, and scalability is conflicting, and the question is, how do we achieve them simultaneously? Our solution to this problem is an energy efficient time modulation for data transmission that we call WiChronos. We propose to encode data in the time difference between two symbols that we call start and stop. This illustration shows a WiChronos transmitter connected to a soil moisture sensor that has recorded a data value of 83%. So 83 is the data that needs to be conveyed to the receiver. To do so, the transmitter sends a start message to the receiver. Upon sending this message, it triggers the timer on and starts counting at a predefined clock. The receiver receives the start message and starts counting at the same clock as the transmitter. Once 83 cycles are up, the transmitter sends a stop message to the receiver. The receiver receives the stop message, stops counting, and the data at the receiver is also 83. Time interval modulation, like pulse position modulation, has been proven to be the most energy efficient in optical networks, but adopting them for wireless networks is challenging, particularly in a wide area network. We design and prototype the start and stop symbols using commercial off-the-shelf components so that the three desired properties of LPWANs is satisfied. Just to recap, WiChronos utilizes ultra-narrow bandwidth for long range. Short anchor symbols and active data transmission in sleep mode help in attaining long battery life and reducing the rate of collisions. We have used off-the-shelf components to prototype WiChronos. Lynx NT is used as a transmitter and receiver, and TI's low-power MSP microcontrollers are used. Our experimental verification was done indoors and outdoors, particularly for longer ranges, and this image shows the location of our experiment. For a small 250 milliampere hour 3.3 volt coin cell battery, WiChronos achieves a battery life of 10 years compared to LoRa, which goes to 5, and Sigfox, which is less than a year due to short anchor symbols. Whatever be the payload size, the battery life of WiChronos stays the same because the energy consumption depends only on anchor symbols. Longer payloads reduce the battery life of the other techniques significantly. WiChronos is able to correct for all timing errors in the payload with 100% accuracy. When there is a symbol error, the anchor symbols are ignored, and so the 100% correctness is only for timing errors when there wasn't any symbol error. The symbol errors are part of the symbol error rate that has also been plotted here. The network Goodput is the total number of successful data bits transmitted in the network in a given duration, and WiChronos performs 3.5 times better than LoRa in a network of 1,000 nodes due to reduced time on air as well as reduced data rate. In conclusion, we propose and prototype a time modulation for energy-efficient, long-range, and scalable networks called WiChronos that achieves a 60% improvement in battery life and allows 1,000 nodes to coexist with less than 5% collision probability under low traffic conditions. I'm happy to answer any questions you may have. Thank you.